Hello, I'm Florian Geißer and I will present our work extending graph neural networks for generalized stochastic planning. First of all, let me say that basically all of this work was done by my student, Ziqi, who did this as his honors thesis project last year at the ANU. The problem we are considering is computing general policies for planning problems. As you probably all know, a policy is a mapping from states to actions and usually represents a solution to a specific planning problem. Whereas on the other hand, a general policy is applicable to every problem of a given domain class. There's been quite a lot of work over the recent years on generalized planning and general policies, and usually those general policies are commonly represented as neural networks. So there are different architectures which support different modeling languages. For example, in classical planning or for SSPs, we have PDDL and PPDDL, and there we have seen, or there are the Strips hypergraph networks architecture and the action schema networks architecture. Whereas for MDPs, we have the modeling language RDDL, and there SymNet and TrapsNet are two possible architectures to represent generalized policies. Our work also introduces a novel network architecture for planning. It builds on the ideas of TrapsNet, but it allows fluence over arbitrary size. Our work is applied to RDDL problems, but it's in principle independent of the modeling language, maybe with slight modifications. And as common or as usual, it allows us to train a graph network on small instances, and then we can evaluate the generalized policy on larger instances of the same domain class. We performed an evaluation on some domains of the IPC of the 2014, which shows quite promising results. So let me introduce the setting that we are considering. So we are considering relational Markov decision processes, first order MDPs, where we have a set of types, and we have state, action, and static predicate symbols, and those predicate symbols basically denote relations of and between typed objects. And as usual, we have a lifted transition function and a lifted reward function, which describes the dynamics of the first order MDP. And given such a first order MDP and a set of typed objects, we can apply our predicates to type consistent objects. This is also known as the process of grounding, and this yields us a factored MDP. One example of such a domain is the elevator domain, where we have two types, floors and elevators, objects of type floor and objects of type elevator. We have state predicates that, for example, describe that a person is waiting on a specific floor for some elevator. We have the predicate that some elevator is at some floor. We have action predicates, which basically describe that we can go up with some elevator, go down, open the door, or close the door. And we have static predicates, which describe the topology of our building. So, for example, is some floor the top floor, which floor is the bottom floor, and which floors are adjacent. Given such a first order MDP, we can then construct a so-called domain graph, which shows us relations between types. Now here's only a small part of our domain graph for the elevator domain. We have type vertices, type nodes. So here, for example, for our type floor, we have one type node, and then we have predicate nodes which corresponds to predicates, and basically we have one predicate node for predicates for some specific argument type. So for example, if we only have as predicate argument one object of type floor, then we have this node here, which corresponds to the predicates bottom floor and top floor. And this node here corresponds to predicates where we have two objects of type floor as argument, which is only the predicate adjacent floors. Now, we can not only generate the domain graph of a domain, but also the instance graph of a specific problem. And the instance graph then shows relations between objects. So for example, given the domain graph and some instance, elevators instance where we have three floors, F0, F1, and F2, this would be the corresponding part of the instance graph. So we have F0 and F1 are connected. So both of these are object nodes, object vertices, and they are connected via some object relation vertex, which basically in this example here states that they are adjacent. And we see F1 and F2 are adjacent. And yeah, so this is basically the graphs that we work on. Those graphs are used in a graph neural network, where every instance graph vertex has some initial embedding, which is a really valued vector. And as usual in graph networks, the embedding at the next step, k+1, is computed by a forward pass over the count network at step k. Now, One problem is that while for object relation vertices, the number of neighbors is the same for over all instances, so we always have two adjacent, or yeah, for the adjacent floors object relation here, we always have exactly two neighbors, but for a single object vertex, there might be different neighbors depending on your instance. So for example, F0 here has two neighbors, F1 has three neighbors, but for another instance, this might be completely different. So we have to deal with vectors with unknown cardinality, and for this we use the attention mechanism. Now, then we want to get a final policy. For that we have an action decoder, which then computes us a distribution over grounded actions. Our empirical evaluation is done on 4 domains of the IPPC 2014. We train the network on data generated from the 3 smallest instances for 4 hours. And since this is only a preliminary study, we compare against the PROST planner. Now, of course, PROST is a domain-independent planner. It's an online planner, so this is not really a fair comparison, but it still gives us some insight on the quality of our policies, right? Because I mean, the PROST planner is still quite a competent planner, so we can see how good does our general policy compare against the policy generated by the PROST planner. And now here are the results. We have 4 different domains. On the right column, we have the average over 100 rounds of our trained network, so our general policy. And on the left, we have the THDS configuration of the PROST planner. In bold, we have instances where one configuration performed in general better. And what we can see is that for Tamarisk and Wildfire and sysadmin, the network, the general policy outperforms the policy generated by PROST. For Wildfire, by quite a lot actually, but also for sysadmin, these values are also quite large, I would say, from personal experience. So I was really surprised when I saw the sysadmin values. On the other hand, in the elevator domain, PROST significantly outperforms the general policy of the network. And we think one reason of that is that for elevator, PROST probably almost generates almost optimal policies. And so we think that the network is still quite far away from optimal policies. And yeah, so which are, yeah, and PROST basically almost has optimal policies for this domain. So still quite interesting results, I would say. And this concludes my talk. So we present a novel network architecture based on domain graphs, which allows for problems with arbitrary predicate size. We have seen that it generalizes quite well across instances of different size. And one interesting aspect that we want to look into further is that in principle, we think our networks are independent of the modeling language used, maybe with slight modifications. So we might also think about whether we can apply this to PDDL or PPDDL. Thank you.